Okay. Now it's a little hard to see what with the small font and everything, so I'll zoom in a little bit. But for right now, what you see is a big table with lots of numbers. The largest numbers are on the left, and those are the counts. And the green lines are the ones that I put in. And so, because in each class, Skittles with you, M&M's with the other. Um, I went ahead and filled in a form as well, and everyone at home should have. Um, in seventh period, there were a lot fewer people in person and a lot more at home, and a lot of those at home sadly did not ever actually submit a result. But so that's the start, and then the second round, third round, all the way up to the count of shakes, in order to get them all. As you can see, some of them, well, there's this bottom line person who just put in dots in order to, I don't know what kind of points they think they're going to get from that, but that is what happened. Then I had somebody who insisted on putting in labels. But anyway, that's seventh period. That's not you. So I'm going to go ahead and clear this up and delete the M's there. Now, I do usually like labels, but they play havoc with spreadsheets. Okay. And then no and A, I'm going to plug in a 0. I don't normally like to change data, but I think you all can understand why I do that. All right, and then what I'm going to do is I am going to freeze this top row here so that as I scroll, it doesn't move. If you don't know how to do that, it's a great skill. It's a great ability to do on Google, much simpler than doing it on Excel. And then I'm going to sort the data. I'm going to select the whole screen. I'm going to sort the data by the number from, I'm going to go greatest to least. Greatest to least. And what that will do is that will then allow me to see who all else had put in my data. And so my data for the first one was 13. So what I don't want to do is I don't want to double count my data because that will not be valid. And so on this anonymous sheet, I am going to delete the data that was the same as mine. Not on the actual answer sheet where I'll assign grades and stuff, but there we go. And I think this second line here is also mine, but they heard me say 9 when I said 5. So those numbers are often confused, and that's why on the radio or the CB you often hear 9er. So that you know, 6, 7, 9er. You guys know that, like on the CB, Citizen Band radio. You guys, any ideas about that? Okay, yeah. So that they know that. So anyway, so I think this is also supposed to be the same thing, and so I'm going to go ahead and delete that as well. Again, for the sake of the graph, I don't want to have any that are, double counted. Now, what I'm going to do as well is I'm going to insert a column here. It's actually just to double check the sum of the ones to the right. And so let me just totally get rid of this row. Okay. And so I'm going to say in this column, it'll be equal to the sum, that's adding everything all together, of what's in column C all the way over to column L. So C2, that's a colon, L2. Hi, Emirates. Okay. And then I could have just accepted that and rounded on down, but I didn't. And then just to double check that the numbers add up. Okay, so sometimes they don't. So let me put in a 0 here. I didn't notice that any before. And I'm also going to narrow this to hopefully get more on the screen. Yep, it is through L. And so anywhere the sums don't match up, then that'll be a problem. And so again, I'm not deleting your data from the actual thing I'm grading. I'm just deleting anything that will cause a problem later on. Let's see here. Oh, we got a lot that problem here. Okay, all right. And I'll just go ahead and delete these rows as well. See how thrilling the life is. Okay. And now I'm going to go ahead and start this all again. Same thing. And they didn't put in anything here. So I'm going to go ahead and count that. It's where it's a mismatch. That's where I question the counting skills. Okay, I question the counting skills. So those of you in the back, can you get off the phone, please? Thanks. All right, so you'll see all these match up, and all the repetitions except for one have been removed. I need to get rid of this. Okay, everything else is not repetitious. Okay, now what I can do is get rid of this word shakes. I did that already. All right. What I can do now is I can make a graph with this data. And I will start with, okay, it's a little slow. I'll start with the big number and go down here. There we go. Morning, Isaac. Right. And then I will go up to insert a chart. There we go. Oh, they're even more customizable. All right, got it. And you'll see here the different lines for the different thingies here. And again, the independent axis here, the horizontal axis, is just each iteration. There's not really like time or anything that we're doing. It's not like every 3 minutes. It's just each time we shook it, where did it go? And you'll see that they kind of follow a pattern here. So we start out with such and such amount, and then we took away these sorts of things as we went down. And it's a nice little curve there. But none of them are really that pretty by themselves. So what I'm going to do is, let's see here. I'm going to drag this over so I can see it more clearly on my screen. And I'm just going to delete the whole chart there. All right. And what I'm going to do now is I'm going to insert one above. Okay. Put this back over here. I just needed to drag it over so I could make sure I deleted the chart easily. All right, and then this is going to be the average, AVG. Okay, and so what I'm going to do is I'm going to add up all of these. All right, average of B3 to B13. Hope this works. Nope. Okay. I'll do it the other way. Unknown function average. Oh, fine. All right, we'll do it the old way. Sum of B3 to B13 divided by, how many would that be? 11? 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. 11 samples. That should be good. All right. And then we'll drag that instruction all the way across here. I know it's kind of ugly with the decimal points, but then I'm going to take that and I'm going to go ahead and insert a graph with just that. Not, there we go. Insert chart. There we go. And look at that pretty, I don't need to edit it at all. Look at that pretty half-life graph right there. Look at that. This is what you did, guys and gals. And again, if you actually look at the numbers, oops, not that. This. Right. If you actually look at the numbers, you'll see 48 rounding here. 48, then 22. Now 22 is not exactly half of 48, but it's pretty close. 24 would be half, right? What's half of 22? 11, right? But you ended up with 10. It's not bad. All right. What's half of 10? 5. Okay, we got 7, so a little bit off. All right, that's okay. What's half of 7? 3.5, which rounds to 4, which is what you had. What's half of 4? 2, which is 1.54 and rounds to 2. Okay, and then half of 2 is 1, and that's 1.45, that rounds to 1. Okay, and then as you go along, it continues to go down. The average continues to go down. There's a little blip here where, because we don't have a lot of data, there's actually ends up being no change, but then it goes down again. But the whole idea here is you can see how if we had you know, dozens more tries, if everybody in 7th period actually turned their thing in. Actually, I would have deleted those two because they would have repeated mine. But there were a few more people in class who didn't turn it in. Anyway, where was it? Oh yes. Then it would look more and more like a half to the power of whatever, you know, half to the power of 1, half to the power of 2, 3, 4, and you know, again, eventually, if you take 1/2 to the power of 10, what is that? Well, what's 2 to the power of 10? I don't expect you to know this. You can whip out a calculator if you want to. What? Well, that's 10 to the power of 2. 10. You'll need to use a calculator. I mean, you can do it in your head, but like 2 to the power of 2 is 4, and 3 is 8. 2048. 2048. And a kilobyte in computer terms, because we use binary things, kilobyte is actually not 1,000 bytes, it's actually 1,024. Small difference, but anyway, so 2048. Is that correct, by the way? Did everyone else use that? Again, just to double check. So anyway, so 1 over 2048. So if I take 48 divided by 2048, okay, then what would I get? I get like 25 divided by 1,000-ish, right? Which would be like 0.25. Is that right? 0.025, excuse me, 0.025. 0.025, not 0.25? You're right, you're right. Okay, so you'll see in the end, 0.18 is a bit bigger than 0.025 because there was this hiccup here where we didn't end up shrinking. But we also have a very small sample size. I mean, out of 11 data points, 9 are 0 and only 2 are 1. You know, really, it would have been better if all of them, you know, had gone to 0 by this point. But oh well. I think, you know, because after 10 shakes, this was the last M&M for me in the afternoon. And I know it's weird. I did actually have 41 particles in both periods just by random chance with that scoop. So yes, Kat. I thought you had something to say. Blow your nose, yes. Just, yeah. I don't have any tissues, but I have paper towels. Well, yeah, I suppose. Yep. Okay, so anyway, that's what I wanted you to see, is that it generally followed that half pattern. And then mathematically did it. I mean, 0.18 compared to 0.025 is pretty far off. but we also have a small sample. But it generally followed about half, 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 half along the way. And that's just a matter of chance. It's the same thing with radioactive materials. It just follows the rules of chance. We don't know which M&Ms will have an M up. It's not like green or Skittles in your case. We don't know if it's green or yellow or red. We don't know if it's this one or that one. We can't predict. But what we can predict is some half is going to do this. Some half is going to do this. Just like we can predict if you have 206 kids born, 100 will be girls and 106 will be boys. Did you know that? There's always a slight extra number of boys born compared to girls. Anybody know why nature would find that useful? What do guys do more than girls on average? I mean, girls do this too, right? They fight, right? They kill each other off. Say again? Peacemaking. Yeah, there's fighting, right? There's killing, right? If you can name 10 murderers, and it's not a very nice topic at 8 in the morning, if you can name 10 murderers, probably 9 out of 10 of them, at least, the ones that you're thinking of, are guys, all right? Oh. Well, there were those high school girls in West Virginia, right? Yeah. Okay. I mean, if you want to think of it, you can think of women too, right? But the tendency is, and that was, yeah, oops. The tendency is in a particular direction. Again, statistically. Not saying this is true for each individual. Just like you don't know particular M&Ms, you don't know particular Skittles. Evidently, I can't remember Juliana's name. I'm sorry, Juliana. I called you the wrong name again. I'm sorry. Yeah. That's very annoying to me, though. Anyway, so you don't know particulars, but you do know in a big group, a certain proportion will do a certain behavior. So again, you don't know which ones. Now, of course, individuals are different than atoms. You do have choice, and they don't. So there are big differences. But in any case, this is what happens. This is what happens. And thank you for this data. You don't get a 0 if I had to delete your data if you recognized your own. But you might lose a point for not really getting it to add up right. That'd be it. Okay. Questions about half-life? All right. So the last section of nuclear chemistry. Last section of nuclear chemistry is section 4. Section 4. Nuclear chemistry in your life. All right. Things that affect you daily. Because you're probably not going to go work. Well, you're definitely not going to go work at Byron Nuclear Power Plant because it'll be closed by the time you'd get clearance to work there. Smoke detectors, though. Smoke detectors use americium. It's not americium. It's a soft C, americium. And guess what it's named for? Well, if you look at the periodic table, the bottom line there, we have our famous friend element 92, which is uranium, and it's named for that planet. And then we have neptunium. Then we have plutonium. We're kind of going outside the solar system. And so then we get the famous planet known as Mars, right? Just kidding. We don't actually have Marsium. Who discovered the New World? I knew somebody was going to say Christopher Columbus. He kept thinking it was India, though. Right? Yeah, Amerigo Vespucci. Amerigo Vespucci. That's why we named it after him, and not after Christopher. Now we're not living in North Christopheria, or well, we are living in North America, and again, Amerigo Vespucci was just a couple of years later. You know, they were both alive. I don't know if they ever actually met, but I mean, yeah, they were working for the same kingdom. They were both Italians. Like, I'm sure they knew of each other. But yes, it was awkward because till Columbus died, he was fighting and saying, "No, this is just the really, really far east. Like, we'll still get to India. Don't worry. Like, we'll find a way." Poor guy. Actually, never mind. Um, so anyway, so we have here amo, which in Latin means I love. And the radioisotope of that is useful is 241, samarium 241. So it's heavier than uranium, does you no harm. It is designed to decay at a particular rate, and it shoots a little bit of radiation over to the other side of the smoke detector. And if there's smoke, then it blocks that radiation. And it's when the radiation is blocked, that's when the smoke detector goes off. So if you have a really, you know, if you're just cooking something in the kitchen and there's a lot of smoke, the smoke detector might go off. It's kind of annoying. You wave it. That clears the smoke away. Then the radiation can continue to go across, and it stops beeping, right? You don't just take the battery out, right? When you're cooking? Okay, good. Yeah. Some people do. All right, so detecting radiation. So how can we detect radiation? So a little bit more about radiation. If you can imagine this, all these radiations shoot off. Am I not sharing? I am sharing. Oh, let me stop the share of that and reshare this. I just thought it would be sharing whatever I had up there, but evidently not. Let me rewind just for a second. All right, nuclear submarine, smoke detector. There we go. All right, so, yep. And chances are that it's much easier for you to buy a smoke detector than it is for you to buy a nuclear submarine. All right, so anyway, so you imagine these things being shot out of a nucleus, whether it is actual things like a helium nucleus or an electron, or just energy, which is the gamma ray. It is going to move electrons away because those electrons that are beta particles are coming in way faster than the regular electrons. Now, because they're going so fast, they can shoot past a lot of the atoms and get into your skin and burn your muscles, but it's not going to hurt your bones. Gamma rays will go all the way to your bones and really mess you up. I mean, if you burn your muscles, yeah, that's ouchy, but, you know, I mean, you might get skin cancer after a while. It's after a while. After a while. Huh? Still cancer. Right. I'm just saying the level of harm is not as severe as like gamma rays, which can give you radiation sickness and you're dead in a week. That is very much directed at particular cancer cells, and that's the whole point. Is it's deadly. It kills those cancer cells that want to kill you. So you say again. It does. Chemo does. Yes, but radiation therapy is different. So just keep that in mind. Radiation and chemo are not quite the same thing. Chemo deals with the whole rest of this class, which is chemical reactions to make the cancer cells die in a chemical way. Radiation, sometimes maybe you've heard of proton therapy. That would be shooting basically hydrogen ions at things, putting it in acid, essentially. So there's all different ways to kill cancer. Of course, the most crude way is just to get out a knife and cut it out, right? But that sometimes leaves stuff behind that will then continue. Cancer is a terrible thing. I'll only say one good thing about cancer. If you get cancer, that means something else didn't kill you first. And we used to have lots of diseases going around that would kill you long before you got old enough to typically get cancer. So
wow, great speech.
Thank you. We have eliminated so many diseases. We've eliminated so many diseases, we now can worry about cancer. Again, the upside, right? All right, we don't have to worry about cholera or getting dysentery on the Oregon Trail or whatever. You know, now we can survive to the end. We're working on the cancer. So anyway, knocking off these electrons. And again, generally you don't want to do this by accident. You only want to do it in a targeted way. So this ionizing radiation is stuff that you do not detect just by looking at it. You can't see a glow. Okay, gamma rays don't glow. The whole point of them is they are much more energetic than visible light. Much more energetic. In fact, if you could see it, you'd be fine because visible light is not dangerous at all. All right. But we need to be able to use devices to know whether there is radiation out there, so we don't send people to their dooms. All right. We need to be able to, just like in the early days of radioactivity, a lot of people got cancer because they didn't realize it would mess up their cells, or at least they didn't realize it well enough. It's one of those things where some people knew, but most people didn't. All right.
How did they eventually figure it out?
Experience, sadly. Just the experience of so many people getting sick who were working with radiation. Eventually people put 2 and 2 together. Oh, we probably shouldn't have those ladies licking the radioactive paint in order to, the paintbrushes, in order to get them to a really fine point so they could draw the glowing numbers on radioactive watches, pocket watches and wrist watches. This was really a thing. The radium girls, if you're not familiar with them, radium, the element up there, Ra. It does glow in the dark. There really were watches that were sold as novelties, because you could glow in the dark. There weren't battery watches at the time, so we stopped that. Again, experience. I say again. I guess it just wasn't quite as good as looking at to a fine point. It is. Well, yeah, I mean to have to lick a paintbrush. That's one of the reasons. Say again, Taylor. I agree, and this is one of the things that made Michelangelo not the turtle, but the artist, probably eventually go mad. He was also doing that a lot with the paintbrushes. Folks, humans don't have to make sense, all right? Even if we can explain them, it doesn't necessarily seem very rational to us. But how many things do we do that people in the future are going to be like, what were they thinking? Single-use drink containers? You know how much that added to the landfills, and birds choked on these things. I'm not trying to blame anybody out there. Okay, this is what the school has provided you with, but it's very sanitary, right? You know that you are the only person who has ever drunk from those boxes, and you're the only person who ever will. For a million years, they will sit in the landfill, and nobody else will touch them. So, and I every so often will have a bottle of plastic bottle of water myself. At some point, people are going to look back at us and say, "What were they thinking? What were they thinking?" So, same thing with the radium girls. What were they thinking? Same thing with people not washing their hands. If you're a doctor, what were they thinking? Again, major reason why dysentery went around and killed so many people. Why didn't they have indoor plumbing? It's not that hard. The Romans had it. Why didn't people 1,000 years later keep it? All right. Why do people stare at screens all day? All right. You just don't know. So radiation, this is how it got discovered, is it exposes photographic plates because we discovered it because the guy had the uranium in the drawer with the film, and so we can use photographic plates or film to detect the radiation. It's not the most effective way. But there are film badges. There are film badges that people who work near radiation wear, and when they get a certain amount of exposure on them, they are required to leave. They're required to leave and not work there again for several weeks until kind of the radiation is worked out of their body. All right, so the americium 241 from before ionizes nitrogen and oxygen in the air. When there's ionization, then you can get a current, electric current, and then they lose their charge when the smoke particles, little bits and pieces of organic stuff, attach to them. All right, and then the current decreases, so there's not enough flow of electricity, and that makes the alarm sound. Another detector is going to be the Geiger counter. Geiger counter with all the rattles. And then I mentioned the film badges. All three are used to know about this, and I'll get into those details another time. I think you've listened to me enough today. So I'm going to go ahead and stop the share, and I'm going to go ahead and stop